The other question we got is, how is surface wind forecast? And kind of what makes it strong and gusty on some days and steady on the other? Well, surface wind, as you might expect, is a really difficult of all the sensible weather elements we deal with, like temperature and dew point. Surface wind is really difficult to predict reliably because it typically is affected by local terrain. Really, really hard to predict something that's on a small scale like that. So ultimately, we can't necessarily predict every kind of wind gust that may occur at an airport. We try to do is give you the understanding of whether this particular case and the magnitude of the wind and the direction of the wind. And we do that through, as meteorologists, through a variety of different methods. Some of the guidance that forecasters use comes from basic experience. A lot of the terminal forecasters that are positioned around the country, they understand the local effects. They know where the airport's located. And as a result, they can forecast for the airport pretty well. You can also look at numerical weather prediction models. They do a pretty fantastic job, especially in the short term, of predicting what the wind is going to be like in terms of speed and direction. And also maybe MOS, model output statistics. Model output statistics are great because they use what's called geoclimatic data. So they use historical information from the particular airport. So when they get the weather forecast model to predict, they can look at that information and they can use the knowledge based on that particular airport's geoclimatic situation. So if it's up on a hill or down in the valley or next to an ocean, that's going to affect what the wind is like. Because it's using historical data from that particular airport, it does a fantastic job of producing, especially in the form of wind forecasts. If you were to look at, for instance, some of the various different forecast models out there, and you can go out and look for the high resolution rapid refresh model, it does a fantastic job because this particular model has a 3-kilometer resolution. So it's 1.86 miles. So a very fine resolution, which from a standpoint of a pilot, that's on the scale of the size of the airport itself. And you can see here that you can see the wind speeds showing up here as well as wind direction showing up. Again, this is at the surface, or possibly in this particular case, it's the 10-meter wind. So it's not really right at the surface, but 10 meters or about 30 feet up, which gives you, again, a good indication of what to expect at the surface in terms of wind speeds and potentially gusts. You can also, again, look at the Localized Aviation MOS program, or LAMP, which is a different spin-off, if you will, of model output statistics. Again, it can show you where the wind is the strongest. So in this case, we're dealing with wind gusts once again, and you can use the legend on the left in this particular case. I produced this particular chart from my own website, but you can actually go out and look for Localized Aviation MOS program, or LAMP, and they will provide that to you there as well. Again, this is wind speeds and wind gust over the next 24 hours or so. So it provides really good guidance at a big weather picture, if you will, for wind gust and wind speed. And it's in this particular case, the MOS forecasts are done at individual airports, but then they can grid this over the entire country. And then you can also see an airport-specific forecast. Some of the various different heavyweight apps out there do provide that. As we discussed earlier, temperature differences drive pressure, and pressure differences drive the wind. And so at first glance here, you might think areas where there's high pressure gradients, you'll see very strong winds. So we have a high pressure gradient up here near this area of low pressure, and you can see the wind barbs are showing pretty significant winds, 30, 35 knots. That's the prevailing wind. That's not even the gust factor added on. And they, again, should be higher there. But let's take a look at the area. Let's just go back real quick and look down here where the wind speeds are, or the isobars are pretty far apart here, but you still see pretty good wind speeds. So There you go. So we still see wind speeds 20, 25 knots in many areas where the isobars are pretty far apart overall. So just because the isobars are close together, that typically means you'll be dealing with higher wind speeds, but because they're farther apart, doesn't necessarily always equate to that. And one of it, you have to look at essentially how winds and why winds gust. So if we look at what's called the planetary boundary layer, that's the area of weather that's typically within the first several thousand feet, maybe as much as 5,000 feet. You go out west in Las Vegas area, it could be as much as 15,000 feet. But essentially, that's that's the area that we're concerned about here. We have essentially what's called the surface layer. That's usually within 500 to 1,000 feet above the surface here. And then we have what's called the mixed layer, where we get most of the mixing, most of the thermal turbulence that's occurring there. Then we have something called the entrainment zone, which is the part that we get into the free atmosphere above. Because we get into this mixing that's going on here, essentially look at this in this particular case, what we see here is that the atmosphere essentially mixes or makes it more homogeneous in terms of the wind speeds. The length of the arrow is the wind speed. So we notice that the wind speeds increase and then they kind of stay the same in this mixed layer. And then they get stronger as you go aloft. So this is the layer that we typically start to look at if we want to estimate what the wind gusts would be. So we typically find the top of that boundary layer, and that can tell us essentially what the strongest winds at the surface could possibly be in the form of wind gusts. So on days where the atmosphere is kind of unstable, where you have a lot of heating going on during the day, that may be actually the result of, again, thermals being produced. So essentially what goes up, something's got to come down to replace it. So you can get essentially some air that's rushing down underneath these that can produce very gusty winds. And where does that come from? Well, that comes from essentially the top of that boundary layer. So we call that mixing down. So the stronger winds at that top of that boundary layer mix down to produce those gusty winds. Notice here, I really didn't tell you that whether or not we're dealing with a situation where we have a high pressure gradient or a low one. In most cases, we can see this even in places where the pressure gradient is pretty minimal, but still have a fair amount of gusty winds, 20, 25, not gusts that come down. So look at that top of that boundary layer. Look at about 5,000 feet up above the ground and look at the wind speeds there. That's probably going to be the maximum gust that you're going to produce.